Hello friends, today I am going to solve LeetCode problem number 2336, smallest number in infinite set. In this problem we are given a set of positive integers. The positive integer starts from 1 and continues until 1000. And we are given, we need to implement smallest infinite set class. The class has three functions: the constructor itself, the pop smallest function, and add back function. In our smallest infinite set, we are initializing our set object, which consists of all the positive integers. And in our pop smallest function, we are removing and returning the smallest integer in our infinite set. And in our add back function, we take an argument and we add this argument, which is a positive integer, to our infinite set only if it's not already present in the infinite set. Else, if it is present, then we don't do anything. Okay, so the constraint also says that the number ranges from 1 to 1000, and there is at most 1000 calls to pop smallest and add back, which means that these two functions are the function that's called most often. Hence, we need to keep in mind to make these two functions more efficient based on time and space, so that it's faster. Okay, now let's look at this example here. Okay, I'll just copy this example, paste it over here so that it's easy for us to look at this thing. All right, so these are the function calls that are made and the parameters passed to those functions, and these are the outputs. All right, so the first function called is smallest infinite set. Well, this is our constructor function that would create our set which consists of all the numbers starting from 1 until 1000. Right now, this set could be an ordered set and unordered set as well, so it depends on what kind of set we are creating. If it's ordered set, then we could just remove, when we are calling a pop smallest, we could just remove the first element, that is 1 would be removed, the next element is 2. So when we remove the first element from the set, and then next element could be 2, right? So basically that's set. But we know in set, can we do like remove from the top or from the bottom? I do not really know about that, but yes, I know that in set we can keep track of like all the numbers are just unique, right? All the numbers are unique in set, all the numbers are unique. Right now, what's told here is that when we add, we only add if it's not present already in our infinite loop, which means that while we are adding, okay, we have this set, we created our, we called our smallest infinite set first, and now we are adding into our set. Now while we add, we are adding the value 2, and we know that when we created our set, we already have the value 2 in our set, right? Because we just created it, so we are not going to do anything. In the next step, we pop the smallest element. Now this set, it looks sorted, right? But what if it was not sorted? We should sort that, right? And for sorting this, since it is of length 1000, then that would be O of basically 1000, which is constant time complexity. But instead of doing that, we are actually going to use a heap. So in that way, we are not sorting the set, we are actually creating a heap. So what we do is, when we are calling our smallest infinite set, we create a set and then we create a heap as well. Okay, but when we are creating these, we do not assign any of these values. And how do we know what is the smallest number? So we are going to create a variable mean value variable which will keep track of the minimum value. So initially the minimum value is equals to 1. Now we are adding to our set, right? Adding a value 2. Now since the minimum value is 1, which means that in our set we have the value starting from 1 to 1000. So adding 2 would just be like, we don't have to actually add 2 because 2 is already in the set. Even though we didn't initialize it, it is in the set because the minimum value is starting from 1. We will only use this set and heap to add those values that are that have already been popped out. So let's see in this example here. So now we are popping the smallest element, right? So when we pop the smallest element, our mean value is now updated to 2. Again we pop the next element, so now our mean value is updated to 3. That is, we the minimum value is 1, we removed that. The next, the most minimum of the remaining positive number was now 2. We remove 2 as well. Now the most minimum of all of the remaining positive integers is equals to 3. Now we remove 3 as well. So the smallest number remaining is 4, right? Now we remove 4 as well. And then the smallest number so far in our set is equals to 5. All right, now we are adding a number. Which number are we adding? We are adding a value 1. So when we add a value, we check with our minimum value. Since 1 is less than 5, that is when we update our heap and set. So we actually we do not need a set, so we just need our heap, and then to our heap we add the value 1. Yeah, we do need our set. So to our set also we add the value 1. All right, now in our next pop smallest, is 5 the smallest or 1 the smallest value? Well, 1 is the smallest value, right? So whenever the length of heap or length of set is greater than or equals to 1, that means that we have some value less than the mean value. So we'll just pop out of our heap. So we remove the element from our heap. Now the length of heap is equals to 0. The set is also equals to 0 because we removed from both of these. Now it's equals to 0. So now what we do is in the next pop smallest, we pop the value 5 and we now have 6 remaining, right? So that is how we do. Now in the next step again we pop 6 and then the smallest we have is 7. Now if we have if there was a function add back with a value 1, then we would again add 1 to our set and 1 to our heap, and again there is an add back with a value 1 only. Then we would check what does the set have the value 1. It already has the value 1, right? So we do not perform anything. So that is why we need our set. We need set to keep track of unique values only. That is, if the value is being added twice, then we like to prevent that, we need a set, we need a heap just to keep like, so that the smallest number is at the top. Basically it is on mean heap, so the smallest number is always at the top and we remove that smallest number. And yeah, we need our minimum value to keep track of like numbers from a positive set 1 to 1000. And yeah, so that's it. Now let's go back to our code and start coding. So we need a set. Initially it's empty. We need a MinHeap. So in JavaScript we know that it doesn't have a MinHeap data structure, right? But LeetCode offers MinHeap functionality library So that is what I'm going to do. I'm going to use that library for JavaScript. So here, new min priority queue. So this will create a min heap in JavaScript. Now I need to pop out the smallest. Okay, we also need minimum value, right? So minimum value is equals to 1. Now if the length of set length gth equals to 0, if it is equals to 0, which means that there is no value in the set and in the min heap, so our mean value is the value that we will be popping out. So what we do is this, that mean value. Okay, we pop. Okay, we are just going to return this, that mean value, and then we do a plus plus. Okay, else what we do is we are going to remove from our heap. So let the value to be removed is equals to this dot min heap dot front dot element. Okay, so this function front dot element will return the element at the top of the min heap, and that is the value that we also need to remove from our set, right? So this, okay, this dot set dot delete the value from the set as well, and then return that value. All right, so that is all about our pop smallest function. Now let's create our add back function. So in the add back function, if the set already has the value num, then we just don't do anything, right? Else what we do is we add that num to our set, and then this dot heap dot enqueue function will insert the element to our min heap. Okay, but we are missing one thing in our add back function. Let's suppose the mean value is equals to 5 and we are trying to add back a value which is equals to 10. So that means that we already have, if the mean value is equals to 5, then we have the value 10 in our set of positive integers, right? Because we have only removed the value 1 2 3 4, right? So in that case we also need to check that, right? So if the set already has that number, then we do not add. Else if the mean val, that is min val is less than or equals to num, that is also when we return. All right, now let's try to run our code and see if it works. Oh, so we are getting an error here. This that set that has is not a function. Okay, so this that set, all right, this should be this that mean. All right, and this should also be new set, because only then in our set object we can access this function. Now let's try to run this. So is it size for set? Okay, so that the set has the property size, not length. All right, so it's accepted. Now let's try to submit this. Okay, so we got a invalid. Let's see, what did we do wrong here? 1 2 3 null null. Okay, so it should return 2 3, but it's returning 1 1. Is this returning me a value 1? Oh, okay, so once we have, yeah, we need to delete the element from the heap as well. So dq, yeah. Cool. Let's submit it now. Awesome. So finally, let's now check the time complexity and the space complexity. Okay, so since we are just creating our set MinHeap and MinVal, it's O of 1 time complexity, and the space complexity here is equals also constant because we have not like set any values to the set or MinHeap, right? And the pop smallest also, this is O of 1 time complexity, and this whole function is also O of 1 time complexity because we are removing from the front of the MinHeap and then deleting from the front, and also delete in set is a constant time complexity, so the whole function is constant time complexity. Space complexity is also constant. And now talking about add back function, it's also a constant time complexity, and since we are adding to a set and MinHeap, so the space increases. If we call this function for 1,000 number of times, so the space will increase 1,000 by 1,000, right? So if we call it n number of times, the space would increase by n. But just looking at one in all, for only one call of add back, adding a set is O of 1, and enqueuing to a mini all is also O of 1. So this whole function is a constant time complexity. So yeah, that was all about this solution. I hope you liked it. Let me know in the comments down below. Thank you.